In this video, we'll talk about the mean value theorem for integrals. So we talked before about the average value of a function, which was computed as the average value of f is the area under the curve divided by the length of the interval in which this is defined. But now we have a new way to talk about this area, and so a new way to talk about average value. So our definition here is that the average value of a function f on some interval ab is average value over ab of a function f is 1 over b minus a integral from a to b f of x dx. The point here is, again, this gives me the area, and this here is the length. So the same idea from before, we just now have this integral to talk about the area under the curve. So why is this an average value? How can we think about it that way? Another reason why is, let me multiply b minus a to both sides here. So we will then see that b minus a times the average value is equal to the integral. But now what do we see here? This here is the area under the curve. But over here, this is a rectangle of width b minus a and height average value of f. So the average value of a function is the height of the rectangle whose area is the same as the area under the curve. And that's why it's called the average value, because it's sort of the average in the sense of it is the rectangle with the same area as this curve. This average value also is a nice property if I have a continuous function. So our theorem says if f is a continuous function in the interval a to b, then this continuous is also integrable, so I can find the integral of this function. Then there is a point c between a and b, so that f of c equals its average value. And this here is called the mean value theorem for integrals. If you look at the statement, the idea of the statement is pretty reminiscent of the mean value theorem for integrals we had before. If I have some properties of my function on some interval, then there is a point c inside such that f of c meets some condition. And we'll see with fundamental theorem of calculus why this is called the mean value theorem for integrals, is because the mean value theorem applied to a certain function. But why does this work? The basic idea is this. Let little m and big M be the minimum maximum values of f on AB. These exist and are achieved because f is a continuous function. Now, what do I know? Well then, 1 over b minus a integral from a to b f of x dx is bigger than 1 over b minus a integral a to b times little m dx, because f is bigger than m on the interval, and this is our comparison theorem. But what is this integral? Well, this is just a constant, so it's going to be m times b minus a. It cancels b minus a's. This is little m. By the same sort of logic, 1 over b minus a integral from a to b f of x dx is less than if I plug in big M. This means my average value lies somewhere between little m and big M. However, f attains these two values, and it's continuous, so by IVT it must hit the average value somewhere on the interval. That's why this has to work. That's why we need f to be continuous for this to make any sense. So in use of this, find a value of c such that f of c equals the average value of f on the interval from 0 to 5 for the function f of x equals x squared. So we found this area previously. We did the whole Riemann sum thing, and we got this area being 125 over 3. Thus, the average value is 125 over 3 divided by 5 minus 0, which is 25 over 3. And now I want to find a value of c so that f of c equals this function. So find c so that f of c is 25 over 3. F of c is just c squared. I can just square root both sides to get that c equals plus or minus 5 over root 3. However, because I'm looking between 0 and 5, I want the positive version there. So my c is 5 over root 3 for this problem. That's the idea of the mean value thing for integrals, why it's true, and how you can use it to find average values for certain types of problems.